We learned last week that if we have two objects and we want to find the force of gravity that acts between those two objects, then all we got to do is use Newton's law of universal gravitation, which says F is equal to G m1 m2 over r squared, r being the distance that separates object 1 and object 2. Now, that force is the force between both of those objects. It could be the force acting on object 1, or it could be the force acting on object 2. You learned earlier on this year, by Newton's third law, if object 1 applies a force on object 2, then object 2 will apply an equal and opposite force on object 1. But what if we have three objects? What if we have three objects beside each other like this, and we want to find the net force acting on number 1, or on number 2, or on number 3 as a result of the other ones? For instance, we want to find the net force on number 1 due to 2 and 3. We know that number 1 is pulled towards number 2. We'll call that F2. It's pulled towards number 2 because of that force of attraction. Now, 2 is also pulled towards number 1 as a result of that attraction, but we don't really care about that because we're not trying to find the force on number 2, not at least in this question. Now, number 3 also pulls number 1 to the right because 1 is attracted towards number 3. Now, 3 is also pulled towards number 1. But again, we don't really care about that one right now because we're not trying to find the force on number 3. In this question, we'd only be trying to find the force on number 1. If you were trying to find the force on number 3 due to 1 and 2, then we would say 3 would be pulled to the left by number 1, and it would be pulled to the left by number 2. That would be another question altogether. If we were trying to find the force on number 2 due to 1 and 3, then we would say 2 would be pulled to the left as a result of number 1. It would be attracted to number 1, and it would be pulled to the right as a result of number 3. It would be attracted towards number 3. But understand, when you solve one of these questions, we're looking at object 1, 2, or 3, not all of them. So you're looking at either the green forces, or the purple forces, or the blue forces, but you're never looking at all of them in the same question. Let's do a question here. 4.3 on page 209, we've got three objects here. In this case, the moon, the earth, and the sun. They're all in a row, which means that in this order, we actually have what's called a lunar eclipse. The earth is in between the moon and the sun, so the moon is essentially in the shadow of the earth. Therefore, we don't end up seeing it. We want to find the net force, in this case, of the moon and the sun combined on the earth. Well, we know in this case that the moon pulls the earth towards it. We'll call that Fm, the force on the moon, the force of the moon, sorry. Now, the moon is pulled towards the earth, but we don't really care about that because that's not the question that we have here. The sun pulls the earth to the right because the earth is attracted to the sun. We'll call that Fs. Now, the sun is pulled towards the earth. The force of the earth on the sun is to the left, but we don't really care about that because that would be another question. What did you do back in Unit 2 in your dynamics unit and earlier on in this unit when you had a vertical circular motion problem where there were two forces acting? You added those forces together. F net is equal to the sum of the forces. But we need to know what the values of each of those forces are first. Well, now we go back to what we did last week. The force on the moon is G m1 m2 over r squared. That's 6.67 times 10 to the minus 11 times the mass of the moon, which in this case is 7.35 times 10 to the 22, times the mass of the earth, which is 5.97 times 10 to the 24. We're going to divide all of that by the distance that separates the moon and the earth squared. When we do that, we should get a value for the force of the moon on the earth of 1.9848 times 10 to the 20 newtons. So a pretty big force, as you would expect. We need a big force in order to keep the moon in orbit around the earth. Now it's for the force of the sun on the earth. For this one, we're going to say I use the same equation, gm1 m2 over r squared, but in this case, m1 wouldn't be the mass of the moon, it would be the mass of the sun. We're going to say that's 1.99 times 10 to the 30. And of course, r is going to be the distance of the sun to the Earth, which is 1.50 times 10 to the 11 meters. Don't forget to square that. We do the math there, we get a value of 3.5218 times 10 to the 22 newtons. Now it's time to combine them, just like we did back in our dynamics unit, just like we did earlier on in this unit when we were solving vertical circular motion problems. We'll say F net is equal to the sum of the forces, F, the force of the moon on the Earth, plus the force of the sun on the Earth. Force of the moon is 1.9848 times 10 to the 20 newtons, and the force of the sun on the Earth is 3.5218 times 10 to the 22 newtons. But here's where we got to be careful about signs. Just like in your dynamics unit, and just like earlier on in this unit, once we sub numbers in, we have to recognize that Fm would be negative because it's to the left, and Fs would be positive because it's to the right. We add those up, paying attention to the negative and the positive, and we should get a value of 3.50 times 10 to the 22 newtons. We end up with a positive value of the net force, which means the total force, the combined force, ends up being to the right, which makes sense. The force of the sun on the Earth ends up being bigger than the force of the moon on the Earth. What I'd like you to do now is take a look at the worksheet that's been handed out to you, the Physics 23 mass gravity problems. Focus on questions 1, 2, and 3, finding the net force on, first of all, object number 1, due to 2 and 3, on object 2, due to 1 and 3, and then on object 3, due to 1 and 2. And then once you've kind of mastered those, or at least semi-mastered those, let's see what you can do with a challenge question, question number 4. In this case, we want to once again find the net force on object 2 due to 1 and 3. But in this case, we have a two-dimensional problem. Let's see what you can do with that, and we'll take a look at it tomorrow when I get back.